We are very pleased to have Dr. Hossein Rafiei Renani here to give us a talk on the stability analysis of slopes, dams, and open pits. Hossein is also an alumni from the geotechnical group at the University of Alberta. He has been also a good friend with me, and he currently works at KCB in Vancouver's office as a geotechnical and rock mechanics specialist. He has over 10 years of experience in analysis, design, and monitoring of major civil and mining structures in many countries. His main interest is in rock mass characterization, failure criterion, advanced numerical modeling, and the probabilistic analysis. And he has published numerous journal and conference articles, and also served as a technical reviewer for a few journals and major engineering projects too. So just a few housekeeping rules before we start. So during this presentation, please keep your mics muted so everyone can hear the presenter. And we will also have a Q&A session after presentation. Please ask your questions by using the chat function. You can either send it to everyone or send it privately to me, and I will try to cover all the questions in Q&A. And also please note that these sessions will be recorded, and the recording will be uploaded to our YouTube channels afterwards. So everyone who are interested to review, you can just visit our YouTube channel. And without further ado, I'd like to invite our speaker today, Hossein, to this virtual stage. Now, Hossein, the floor is yours.
Thank you very much, Lan. It's a pleasure to be back to the University of Alberta and share some of what I have learned in the past with my fellow students and professionals who have joined this meeting. Welcome, everyone. If you can please confirm that you can see my screen, I can proceed.
Yes, I can see your screen very well. Can you make it in presentation mode? Yeah, great.
Okay, perfect. So it's a pleasure to be here. Welcome, everyone. Today, I'll be talking about stability analysis, which is a big part of what all of us geotechnical engineers have to do as part of our professional practice. And it can be an important responsibility, and a lot of considerations have to be taken into account for doing these kinds of analyses. So today I'll be talking about slopes, dams, and open pits. And after I wrote this title, I realized that I'm going to be covering a lot of different grounds. So it's a very tall order, and each of these subjects can be covered in a full course or many books. So what I'll be presenting is just a very brief on each of these subjects, and it's not going to be extensive and exhaustive. Just some parts of each of these problems that have been interesting to me and I wanted to share with you today. So before I proceed, I'd like to acknowledge some outstanding individuals who have contributed to my growth professionally and personally, and they have also informed some of the ideas that I'll be presenting today. So I'd like to acknowledge Dr. Derek Martin and Norbert Morgenstern from the University of Alberta, and Dr. Everett Hook, Dr. Ming Kai of Laurentian University, and also Dr. Lauren Lorick and Pedro Varona of Itasca, and also my colleagues at Klohn Crippen Berger, SNC Lavalin, and also BC Hydro. Now, what I'll be presenting today are my views, and they may not represent the views of any other individuals or institutions that I have represented in the past. So without further ado, let's jump in. So I'd like to start by giving you a visual representation of what it is that we will be discussing today. And let's see. Bring this here. So this is a picture of Hoover Dam on Colorado River in the United States. And it's a gravity arch dam. And when it was built, it was the largest concrete structure in the world, and still is one of the largest structures of its kind. So as you can see, it's going to apply a lot of forces on these abutments, which are made of rock. And also downstream of that, we have some structures which are founded on rock slopes. And then we have another bridge, which is also abutting on these rock slopes. So these are some of the problems that we have to consider when we do stability analysis of dams and slopes. And this is another view of the same dam, the Hoover Dam, just downstream. So what you see here on top is the Memorial Bridge, which is about 270 meters high. And also down here, you see the power plants for the Hoover Dam and also the emergency outlets. As you can see, they are founded very close to the rock surface. So it's imperative that this rock slope is stable and safe and does not move, because these are very critical structures which cannot tolerate a lot of movement. So the confidence that's needed to design these rock slopes has to be very high. And this dam and these structures have been performing well over the past 100 years or so. So that's an example of a successful design. And this is another example. So this is White Canyon West in British Columbia, and we have the CN Trail here. You can see that it's going very near the toe of a very high rock slopes. And here you can see the train going through the loops. So again, it's a very important route, and it's very important that these rock slopes stay stable and don't pose undue risk to the rail. And lastly, this is an example of an open pit mine, the last subject that I covered in the title. So it's a Chuquicamata in Chile, and it's really hard to communicate the extent and volume of this open pit mine. It's about 4 kilometers long, about 3 kilometers wide, and about 1 kilometer deep. It's a very huge man-made structure. And again, here we have a lot of ramps, a lot of operations, and a lot of equipment. And it's imperative that these slopes be performing well and don't show signs of unacceptable instability. So again, that would be one of the topics and structures that we will cover today. Okay, I just want to confirm this bar that I see below, is that blocking your view of some of the pictures, or you see it without any?
No, there's no obstacles. It's perfectly clear.
So
yeah.
So it's only on my screen. Perfect. Okay, so let's look at some sliding mechanisms in slopes and open pits. So for example, going from the left to right, here we have a rock slope where we have some pre-existing weak planes, which are shallower than the dip of the slope face, the cut face, but they are steeper than the friction angle of this discontinuity. So they can flow out. So this is what we call a plane failure. And this is another view of a plane failure when we have a tension crack in the back, and water can get into this tension crack and push the block out. So some examples of a plane failure. Here we have a form of rotational failure. Now this can happen in soils and landslides. It can also happen in weak rocks, such as clay shales. So that's what we call a rotational type of failure. Here we have an example of a translational failure here. So it's quite thin in this example. So this is quite similar to what we analyzed as an infinite slope, and it's happening in some form of a weathered rock or soil. On this area, you see an example of an open pit, which is quite high and steep. And you see 2 gray lines representing a range of piezometric levels within that open pit. And we see a potential failure surface. So the scale of this rock slope is so high and so large, and the spacing of discontinuities between the toe and crest are so little that this whole mass can be considered as one uniform continuum. And we can consider this kind of circular type failure in it. And lastly, at the bottom here, I'm showing an example of a wedge failure when we have 2 intersecting features creating a line of intersection which can daylight out of the slope face. And again, it's steeper than the friction angle of the surfaces, so it can slide out. This is the type of failure that we may observe at the scale of individual benches within an open pit mine or near a cut in rocks. As you can see, there are many different names and many different geometries, but as I'll mention later, they all have one thing in common. Now let's look at some dams, sliding mechanisms in dams. So first we have an embankment dam, typical geometry here. We have a reservoir here, and then we have our tailwater at a lower level downstream. And you can see a potential sliding mechanism long term, which is going through the body of the dam. So this is again very close to a circular failure of the dam itself. And down here we have another example. This is an actual tailings dam which has failed, unfortunately. And as you can see in this case, the dam itself has remained in good shape. It has not broken or failed, but the tailings behind it and the foundation underneath it have failed and moved. So it's possible that the failure surface does not involve the body of the dam itself, but it goes through the foundation and breaks out. So this is another example of a dam failure mechanism. To the right, we have a typical concrete gravity dam. In this case, it has a sloping base. And the forces that we have here is essentially for static conditions. We have the hydrostatic force of the water here. We can consider an active wedge, which is going to again push this block of concrete out. And then on this side, we have some passive resistance from these passive wedges here, and also some water pressure from the tail race water. In cases where we are going to consider seismic stability of this concrete structure, we will add the hydrodynamic forces of water, which are usually taken as Westergaard pressures. And we also apply a coefficient of seismic acceleration to the body of all of these solids, which is in relation to the peak ground acceleration for the earthquake that we are considering. And again, we can do the analysis with those additional forces. So again, these are some very different failure mechanisms, but they all have one thing in common. What do you think that is? In all of these, we have started with something which was not moving, and then when it fails, it moves. So we go back to our first law of motion, which says an object at rest remains at rest unless it's subjected to an unbalanced force. So that's the first Newton's law. And this unbalanced force is going to destabilize the system and make it move. So the way we define the unbalanced force is the total driving force, which is going to make the system move, minus the total resisting force. So obviously, if the resisting force is higher, there would be no instability. But if the driving forces are higher than resisting forces, then they can overcome them and cause the system to move. So what we define here is the factor of safety, which is essentially the ratio of resisting forces to driving forces. This is a comprehensive definition of factor of safety, which can be used in many different applications. And it's also used by many organizations such as the US Army Corps of Engineers. Now, for some cases, we can have an alternative definition of the factor of safety, which would coincide with this. So if we have an unreinforced slope, meaning there is no rock pools or anchors or dowels or geotextile or geomembranes, so it's just the soil itself providing all the resistance, then this resistance is going to come from the shear strength of the material. So we can essentially divide the numerator and denominator by the surface area of the slip surface and make it like this. So the factor of safety would be the shear strength on the slip surface divided by the shear stress on the slip surface at equilibrium. So these two will coincide when we have an unreinforced slope and all the resistance is coming from the shear strength of the materials on the slip surface. However, if we do have some reinforcement, then this equation has to be modified to the more comprehensive equation to calculate the factor of safety. So that would be, for example, in a case where we have a dam and we need to stabilize it using some anchors or piles or what have you. That's when we use this kind of definition. But for many pure geotechnical applications, for example, if we are just looking at the body of a dam or embankment, which is not supported, this definition is adequate. Okay, so now how do we calculate this factor of safety? There are different methods, obviously. So let's start with limit equilibrium analysis of wedges to begin with. So limit equilibrium analysis considers the condition of the system at the condition of limiting equilibrium, meaning at the point where it's about to slide, but not yet, where those forces are at equilibrium. So we can have, for example, a single wedge analysis. For example, this is one example where we have a concrete gravity dam just sitting on a flat bedrock. There's no bedrock behind it, and there's no bedrock in front of it to act any active forces or passive forces on the concrete block. It's just a rigid block, essentially. And again, the forces are the hydrostatic or hydrodynamic forces of the water behind, some uplift at the base, because here we have a transition from the reservoir pressure head at this point, which is represented here, to essentially no pressure head at this point. So if we don't have any drainage system, it's going to be something close to a linear transition from reservoir pressure to no pressure. And then we obviously also have the normal force plus the uplift to counteract the weight. And then that's essentially this the free force body diagram of the system. Now, this is another example where we have a rock slope and it has a tension crack. Again, we have only one wedge, one block of rock which can move. Again, water is in the tension crack and it can come out at the toe. So we have this kind of linear transition of uplift pressures, and we consider the normal and the horizontal and vertical forces on the block and calculate its stresses at equilibrium, also calculate its strength on the slip surface based on the cohesion and friction angle, for example, and then the ratio of those will give you the factor of safety. Now, we can have a more complex situation where we do multiple wedge analysis. For example, as I mentioned, if the base of this concrete gravity dam is locked into the foundation, to the bedrock, then we can consider multiple wedges. So for example, if we have one top layer and then another layer behind, we can divide these wedges by this elevation. So we have the first little wedge and then another wedge, which is right behind the body of the dam. And then we have our passive wedges, one here, represented by wedge number 4, and then the last small piece, wedge number 5. And again, we calculate equilibrium for each of these individual pieces, and we make them all at equilibrium, and we calculate a factor of safety for all of these slip surfaces. So the slip surfaces would be this piece, plus this piece, plus this piece, plus this piece, plus this piece. Now, this is coming from US Army Corps of Engineers method. And as you can see, they do not consider any shear forces between the individual wedges. So it's only normal force. And that's a measure of conservatism that's embedded in their method. Okay, so now let's look at another method, limit equilibrium method of slices. So in this case, for example, if we have an embankment or a soil slope or a landslide, and they are not exactly rigid wedges. They can be better modeled using limit equilibrium method of slices. So in this case, as many of you may know, we divide the sliding mass by a series of slices and consider the equilibrium of each of these slices. And we consider that on the base of slip, on this close to circular path, we have the same factor of safety from top to bottom. And by calculating that factor of safety can be obtained. So we have many different types of method of slices over the years, starting from ordinary to Morgenstern Price and some more recent ones. You can see that not all of these methods satisfy all conditions of equilibrium for these slices. So the methods that do satisfy both moment equilibrium and force equilibrium on this table are Spencer method and also Morgenstern Price method. The general limit equilibrium method is also something which is essentially very similar to the Morgenstern Price method and has been introduced much later. So essentially, I refer to it as the Morgenstern Price method. There are other methods which are not on this chart, but for most practical purposes, we usually use the Spencer method or Morgenstern Price because they satisfy moment equilibrium, force equilibrium, and they also consider an inclination of the normal force and shear forces, so they are taken into account. However, they are not known. So for the Spencer method, we consider that the inclination of shear forces versus normal forces between the slices are constant, going from one end of the sliding mass to the other. In the Morgenstern Price or general limit equilibrium method, it can be variable, but again, it's defined through a function. For example, it can be half a sine function or trapezoid function or many different types. But that's an assumption that we need to make for limit equilibrium methods of slices to make the system determinate and be able to solve all of the equations. So let's step back and see what are the main benefits and main disadvantages of a limit equilibrium method of slices. So the first advantage is probably that it's very simple and quick, and it requires few input parameters. So essentially, once you know your loads and the densities of materials and shear strength parameters, cohesion or friction, or if it's nonlinear Hoover-Brown parameters, you're good to go. And many engineers are familiar with this method, so there's less risk of making mistakes in the process. However, there are some disadvantages which in some cases may be quite important. These limit equilibrium methods do not provide any information about displacements. So usually when we consider any structure to be designed, we have some stability limit states, which consider the stability of the system, which we call them ultimate limit states. We also consider serviceability limit state, and those have to do with the amount of displacements or deflections which are induced in the system. So by virtue, this limit equilibrium method cannot help us with serviceability because it cannot give us any information about displacements. It's only for ultimate limit state considerations. So it just gives us the factor of safety. Another important limitation in some cases is that it neglects the effect of strain on strength mobilization in different materials. So let's, for example, consider that we have a geometry like this. So the concrete is in firm contact with the bedrock here, but we may have some loose material at the toe of this concrete gravity dam. So the amount of strain that takes to mobilize the strength at the interface between the concrete gravity dam and the bedrock may be very little, but the amount of strain that takes to mobilize the passive resistance of, for example, a granular fill may be much higher. So these strength values that we usually use as ultimate strength values, and they are not strain compatible. They are not mobilized at the same strain. It is very possible that after slip has occurred on one interface, the strength on another interface mobilizes. So the way we currently do with limit equilibrium analysis, neglecting the effect of strain, may not be quite correct in some cases. Another drawback in my view is that it requires a trial and error search algorithm to find the critical slip surface. And that can be quite challenging for complex systems. If we have just a simple slope with one material, it's quite easy, and the search algorithms can quite easily find the critical slip surface. However, if you have multiple discontinuities, a complex topography, and multiple materials in the slope, it can be quite an extensive and manual process to try different types of slip surfaces that you define as a user and find the most critical for yourself. And sometimes a modeler or engineer cannot find these most critical surfaces. I have reviewed many hundreds of stability analysis, and in most of them, by more close look at the model, I have been able to find more critical slip surfaces. So this is a non-trivial concern for complex systems. Now, the other drawback in my view is that it assumes the same factor of safety for all slices. Again, when we have a complex system made up of different materials, it may be possible that the strains are initially concentrated in one part of the system, overstressing them, and then propagate upwards, something close to a progressive failure. So the factor of safety may not be equal for all the portions on the failure surface. Another drawback in my view is that we have to assume some formulation for the inclination of slice inter-slice forces in the method of slices. And last but not least, this is quite important because now we are seeing many more 3D software, essentially using the same limit equilibrium equations, expanding them to 3D and providing some really interesting results. But we have to be aware that these methods are less developed for 3D analysis, and I will touch on that a little bit later. There is another method that we can use, and it's called shear strength reduction method to calculate the factor of safety of a system, whether it would be a tailings dam or a rock slope or a soil slope or an embankment. And there are a few steps. So first of all, we have to do a proper stress deformation analysis of the system with the original parameters of the system that we know are representative. Once we bring that system to equilibrium, then we go through that shear strength reduction algorithm where we divide the shear strength of the material by a strength reduction factor. So as you can see, generally we can specify shear strength as a cohesive component and a frictional component. Here I have written it as a Coulomb type linear slip criterion. However, even if it's non-linear, we can translate it into an equivalent linear form. So this method still holds for nonlinear failure surfaces as well. So essentially we divide the cohesion and tangent of friction angle. By doing so, you can see from this equation that we are essentially reducing the shear strength by that strength reduction factor. And we see if we reduce those cohesion and friction angle values to some new values, do we still reach equilibrium of the system or not? So if we still reach equilibrium with those reduced values, we can reduce them further. So we go to step 3, readjust the SRF value, the strength reduction value, to a higher number, and we repeat this process until we reach a situation where we can no longer get a converged results. So in the context of stress deformation analysis, we can consider that when the model converges, we have an unstable system, and when it does not converge, we have an unstable system. So where that transition happens is our state of limiting equilibrium. So the SRF that corresponds to that transition between convergence and divergence, we call it critical strength reduction factor. Now, it's very interesting. Note that the definition that we have provided for critical strength reduction factor is exactly identical to what we presented for the factor of safety in limit equilibrium analysis. It's exactly the same factor by which we have to reduce the shear strength of the materials to get to a condition of limiting equilibrium. So in terms of definition, they are exactly the same. However, the former, the critical strength reduction factor, is obtained from a more complete method of analysis, which considers fully the conditions of equilibrium, strain compatibility, and also constitutive behavior of the materials. So in limit equilibrium, we satisfy some equations of equilibrium or all of them, but we do not satisfy strain compatibility or constitutive behavior of materials and calculate the factor of safety. With shear strength reduction, we consider all of them and use the same definition to calculate the factor of safety. So if this method is applied correctly, in my view, this represents a more accurate value for the factor of safety. Now, here I have presented two examples of shear strength reduction works that I have performed in the past. So on the left, you see an example of an excavation in 3D that I have cut so we can better see the distribution of displacements and the mechanism of failure. So here we have some lines, if you pay attention, which represent some weak layers. So we have two of them at two different elevations, and then the bottom of the excavation is below. And as you can see, this model has quite accurately predicted a reasonable failure mechanism, considering both of them in one model and showing that slip on the lower weak plane is more critical and has provided a factor of safety. Now notice that we have a very fine and sophisticated mesh for this model. It's important to have this kind of mesh when we do 2D or more importantly, 3D strength reduction factor, because the results do depend on the accuracy of the model, which is affected by the quality of the mesh. To the right, I have a model that I built for an open pit mine. So we have the entire open pit in our model. We have all of the inter-ramps, and I have performed the shear strength reduction calculation for it. And for example, we can see that the slope on the right wall is more critical. It's showing more displacement. So this can indicate to us that we should expect more displacement and we should have more stabilization measures on the right wall of this open pit. Now let's consider some advantages and disadvantages of shear strength reduction method. So in my view, the most important advantage is that it calculates displacement. So we will have one model which can help us with stability and serviceability considerations. So this is very important because we have no way to measure the factor of safety. There is no way to measure the factor of safety, I repeat. So that makes it hard to verify any number that we get out of limit equilibrium analysis. We can see that the system is stable. Sorry, give me 1 moment. So if we have a stable system, we know that the factor of safety is over 1. If we have an unstable system, we know that the factor of safety is less than 1. But we have no way of knowing, for example, if the factor of safety is 1.3 or 1.5 or 1.1. However, we can always measure displacement at the surface of slopes or open pits or dams, and also within them. So we can use those information, measure displacements to calibrate our models that we have used for shear strength reduction method. So that gives us more confidence in our calculations. Another benefit is that the critical failure mechanism reveals itself in the process. We do not have to do any secondary search for a critical subsurface as we have to do with limit equilibrium analysis. The system automatically calculates all the stresses everywhere in the system and finds the most critical in the process and reveals it at the end. We can capture the constitutive behavior and strain compatibility of the materials because during the process, all of those are considered and solved. And it's also possible to exclude some materials from this shear strength reduction algorithm. As you may remember, I mentioned that in limit equilibrium methods, we have to assume we have the same factor of safety for all of the materials on the slip surface. With shear strength reduction method, we have the option to exclude some materials from shear strength reduction. They can still be present in the model, but their strengths are not reduced. So for example, if we have a case where we have a weak layer or weak material for which we have used a lower bound value of strength, and we do not want it to be reduced any lower, we can assign that lower bound value and exclude it from the shear strength reduction algorithm and calculate the factor of safety. So that's another capability that some limited equilibrium analysis cannot provide, and shear strength reduction method provides. And last but not least, as we move towards a more sophisticated 3D analysis, we have to keep in mind that with shear strength reduction method, it's equally well developed for 3D analysis as it is for 2D analysis, because all of the constitutive models and equations of equilibrium are the same, solve the same. So we have the same confidence. As long as the modeling is done properly, we have an equally good result from a 3D analysis. And the main disadvantages that I can list is that it takes longer, with emphasis, sometimes much longer, to build a good, reliable model and also to solve it. Another disadvantage is that it requires a modeling skills and expertise, which may not be available in all institutions or consulting firms or by all engineers. So you need some skilled individuals to perform these kind of calculations for important projects. And last but not least, it requires more information because we are considering displacement. So not only we have to provide unit weights and strength properties, but also stiffness values for all the materials and interfaces in the system, and also the in situ stress regime. In limit equilibrium methods, we assume that everything is gravitational, and we do not specify anything for the magnitude of horizontal stresses. However, with shear strength reduction method, we have to specify it, but in the process, if it has any effect on the stability, we can capture it. Okay. So how do the results compare in 2D between these two methods? In my experience, limit equilibrium analysis and strength reduction method give similar results when we are dealing with 2D analysis of simple slopes. So where the slope geometry, topography is simple, and the material, it's maybe homogeneous, or we have two materials, but the slip surface is quite smooth. In these cases, we get quite similar results from these two methods. So for example, here I have used a finite element model to calculate the factor of safety with shear strength reduction, which is 1.24. With limit equilibrium, it's 1.27. So for most practical purposes, they are the same. However, if we have complex geometries, or where our material behavior is complex, or where we have a slip surface which has some sharp changes. So for example, here is close to a 2D section of the previous 3D model of the excavation that I showed you. We have part of the slip happening on the weak bedding plane, which is quite straight. And then we have a sharp change into the failure of the material above. So we have a hybrid failure mechanism. As you can see, we can get substantially different results. So in this case, limit equilibrium gives us a factor of safety of 1.86, whereas shear strength reduction gives us 2.16. Now, what happens when we go from 2D to 3D? Again, in my experience, as long as the slope is the slope geometry is simple, materials are simple, homogeneous, or close to it, the results are going to be similar in many cases. However, if we have complex systems, the result again can differ significantly. And I have also noticed that in some cases, 3D limit equilibrium methods have to accept some amount of tension at the base of some of the columns to give us reasonable results. And here I have one example of that. So let's assume that we have some vertical beds. So let's say we have a folded formation and the top of that fold has been eroded. And what we have been left with is something close to vertical layers near the surface. So, and this is a weak layer, and on either side of it, we have some stronger layers. So essentially a slip is going to happen within this weak layer. Normally, when you start, you want to have no tension at the base of any of your columns. So columns are essentially the slices which have been extended to 3D. So slices become columns. So when we do not accept any tension, limit equilibrium factor of safety for this system is 2.94. And you can also see that the failure mechanism is quite unrealistic. It has a shallow backscarp and it's daylighting mid-height into the face of the cut, which doesn't make a lot of sense. If you accept some amount of tension at the base of some slices, so for example, if you allow 4% of the slices to have some tension at their base, then your factor of safety comes down to 2.37. And you can see that the failure surface has become much more reasonable. Still, if you allow more slices to have tension at the base, your factor of safety will be reduced to 1.17. And now you can see that the backscarp is very steep. So essentially, the tension that we are getting is at the backscarp. And as we allow the system to have more tension on some of the slices, the backscarp can become steeper and steeper, which in reality, it is very steep for this kind of situation. So we have to accept some tension. However, in reality, we know that soil materials, such as what I've assumed for this weak layer, cannot accept much tension. So this is something that we have to keep in mind as we go through 3D limit equilibrium analysis. However, for shear strength reduction method, you don't need to play with any secondary parameters which are only related to the method of calculation. You just build your model, specify your material properties. There's no search algorithm. There's no acceptance of tension. Everything is fully specified and fully solved. And you get a factor of safety of 1.18, and you get a very reasonable sliding mechanism. So in my view, if we have complex systems, we have to be very careful with what we get out of 3D limit equilibrium analysis and check many different search algorithms, check the effect of tension at the base, and make sure that we are getting something which is reasonable. In my view, shear strength reduction method for complex problems in 3D is going to give us a more robust answer. However, it's going to take time. All right, let's move to incorporation of strain softening. With limit equilibrium analysis, we can only assume one set of strength parameters because we have no displacement. So we specify one value for cohesion, for example, and one value for friction angle, and those are the values that are going to be used in the analysis. They won't change during the analysis. However, in many cases, we have strain softening materials. So for example, this is one case of yellow clay reported by Skempton, where you can see at different levels of confining pressure or normal stress, we go up, we reach a peak, and then we come back. This is what we call strain softening. With increasing strain, the capacity of the sample reduces. So this would be our peak, and this would be our close to post-peak. And if we continue this strain long enough, we get to residual. So for each level of normal stress, we can get peak values and residual values. And if we plot them, we can get something like this. So this is done for a blue clay reported by Alonso and Jens. So we can get one failure envelope for peak strength of the material and one for residual strength. And the question is, what do we do with this? In limit equilibrium analysis, we have to choose one set. And what usually has been done is that the peak values are chosen. However, we understand that that can cause some unconservative design, and in some cases, it has resulted in failures. So how do we solve this problem? How do we take this kind of behavior into account when we do limit equilibrium analysis? The answer is that we can't. We can, however, incorporate it within the framework of a full stress deformation analysis, as we do with shear strength reduction method. So for example, here I have shown the slope, which is made of material which is a strain softening. So we have our strength parameters starting from a peak value, and then as our plastic shear strength increases, they will be reduced, and then after some point, they get to a residual value. So those will be for both cohesion and friction angle. We go from peak values to residual values as plastic shear strain increases. So if we assign such behavior to the material inside the slope, these are the kinds of responses that you can see. If we apply some normal force to the top of this slope, we can see how the load displacement behavior differs from a perfectly plastic model. So I have shown here PP stands for perfectly plastic. So as we increase the vertical stress, which is applied here, we can see that vertical displacements increase. And after some point, they will plateau because we have a perfectly plastic model. And that's what perfectly plastic means. It works also in the framework of the slope. However, if we have a strain softening material and we apply displacements or velocities at a constant rate to the top of the slope, this is the type of behavior that we see. As we increase the displacements, we follow the same path for loads on this strip. However, before we reach the peak for perfectly plastic material, we deviate from that line and we see this kind of strain weakening for the overall slope as well. So strain weakening behavior, the same type of trend that we see in the lab, will also be observed when we have the slope, which is made of such material. I have also shown on this plot normalized failed length. So if the total length of failure is 1, how does it develop as we increase these vertical displacement? As you can see, initially, as we increase the displacement, the rate is slow. But beyond a certain point, when we get close to these peak values, they will skyrocket. So this is something that we see when we have sudden failures in slopes or in tailings dams. In many cases, inspections have been done a few days prior to the failure and nothing has been observed, and suddenly we have a failure on our hand. It's because of this type of skyrocketing of displacement. So how do we incorporate this into the context of factor of safety? Essentially, we can do the same thing that we have done for perfectly plastic models. So for perfectly plastic models, our strength parameters, C and phi, tangent of phi, are constant. They do not change with shear strain, plastic shear strain. So if you draw them here on this kind of plot, you'll have some horizontal lines. So if, for example, our initial representative values are here, when we apply a strength reduction factor, they will be reduced. So for example, this line for a given value of SRF will come down to this line. And then we check if it's stable or not. If not, we decrease it further. And we can do the same where we have a strain softening material. However, they are not going to be horizontal lines. As I mentioned, we will have a decrease initially, and then we get to a plateau. Now, this plateau can be, for example, 0 for cohesion, but can be a non-zero value for friction angle, as it is. So, for example, if for a strain softening material, we have this kind of trend initially, with a strength reduction factor greater than 1, it will be reduced to something like this. So we can do the same exercise that we have been doing for perfectly plastic models for strain softening. So this is an algorithm that we published to kind of establish a framework to calculate the factor of safety for slopes or systems with strain weakening materials. And on the right, you can see the effect. So these two lines are for perfectly plastic model. So we have a slope. In this case, we do not have any loading on top. It's just the gravity loading of the slope itself, as it is in reality in most cases. So as we increase our shear strength reduction factor, you can see that our displacements increase very, very slightly, but after a certain point, they will skyrocket. And after this point, we don't see convergence anymore. So this could be something close to our factor of safety, close to 1.55, for example, for the perfectly plastic model. And if you check it for a fine mesh, as I have here, or a medium mesh, so those refer to the size of the elements within the system, the difference is very small. However, if you do the same exercise, however, for a strain softening material, we get something like this. So the squares are for the medium mesh, the circles are for the very fine mesh that I have shown here. So as you can see, we follow the same path, but at a much lower value of strength reduction factor, we get to a condition of no convergence. So our factor of safety is much lower compared to what it is for a perfectly plastic system. And you can also see that for the fine mesh, our factor of safety obtained is smaller than what it is for the medium mesh. And so we always have to be very careful with the mesh resolution when we are working with strain softening materials. And I've seen many models where this consideration has been completely ignored. And in many cases, the results will be essentially useless if we don't pay attention to it. How can we use this? We do have slope design charts for perfectly plastic slopes from limited equilibrium analysis, for example. But how can we help our engineers to use these kind of methods and apply them to cases where we have strain softening materials? What I have done here, and it's been published, is that I have introduced a kappa factor, which is the factor of safety ratio. It's essentially the factor of safety of the strain softening system to the factor of safety of the perfectly plastic system when we use the peak strength values. And I have done a series of analyses for different slope angles and different values of peak cohesion and peak friction angle. And I have considered two scenarios. In the first scenario, our residual cohesion is 0, but our residual friction angle is similar to our peak friction angle. So essentially, let's say if it's close to something like a sand, we don't lose a lot of friction angle, but if there's any interlocking at the very beginning, and that's destroyed. Or if, for example, we are dealing with a rock sample, that can be reasonable. So this is close to one end of the spectrum for strain softening, where cohesion goes to 0, but friction angle stays the same. And for this scenario, I have considered different slope angles from 30 degrees to 75 degrees with different values of cohesion and friction. And these are the trends that we see. And I have been able to develop this equation to help engineers do an estimate of the factor of safety for a strain softening slope when they only have the factor of safety for the perfectly plastic system from standard methods, and they can assume this scenario. I have also provided another chart where for scenario number 2, where the friction angle is also reduced to half of what it is for peak. And again, you can notice that in most cases, they will get close to something between 0.4 to 0.6 of the perfectly plastic factor of safety. So these can be used. Now let's move to acceptance criteria. How am I doing in terms of time? Let's see. Okay, very close to the end. Okay, so I'll wrap it up here. Just one word on acceptance criteria. We have many different authorities giving guidelines. So here, for example, we have guidelines of the US Army Corps of Engineers for new earthfill and rockfill dams for embankments and slopes. So end of construction is unusual. So we have a factor of safety of 1.3 or higher. For long term, it's higher than 1.5, and rapid drawdown can be between 1.1 to 1.3. We have similar guidelines for open pit slopes. And on the right-hand side, I have provided some guidelines for concrete structures from the US Army Corps of Engineers. So there they divide different loading conditions to usual, unusual, and extreme based on the annual probability of those happening. And then they also divide the structures into critical structures and normal structures. And critical structures are those whose failure can cause loss of life. And for these structures, they have higher requirements for factor of safety. So you can have these for your records. So with that, I'll wrap up and open the floor to any comments or questions.
All right. Thank you a lot, Hossein, for sharing your research. And it's very comprehensive and also covers lots of fundamental elements. And it's a very good refresher to me. You also provide some state-of-art understanding, for example, like strength reduction methods that applies to the stability analysis. So as you are actually here close to 1 o'clock, if you have to leave now, you can follow up Hossein with your questions via email. And I think he's more than happy to answer your question. So currently, I only have one question that's sent to me. So the question is, what are the go-to guidelines used for Canadian dams stability review? Is it FERC? I think it refers to Federal Energy Regulatory Commission, or local national guidelines.
Yes, it's usually local guidelines. So for example, in Canada, Canadian Dam Association provides guidelines for us.
Okay, thank you for your answer.
Engineers have provided many design manuals for different types of structures, and those are also used widely abroad.
Okay, thank you. And the other one just sent right now, it is what software was used for strength reduction method in your example, I guess.
Yes, so I have used Flag 2D, Flag 3D, and RS2.
Okay, great. And so I don't really have any question coming up. Oh, actually there are 2 more here. So for the scenario 2, he didn't say any equations between 30 and 40.
Yes, that's correct. So essentially, these are the type of data that we have for scenario number 2. For the case where we have a slope angle of 30 degrees, the results are all pretty much close to 0.42 for the factor of safety ratio. But when we go to 45, initially for very small values of peak cohesion, they show an increase and then they go back to a lower value. So you can imagine something of a transition between 30 and 45, going from horizontal to having a small peak, a higher peak until we get to here. So one thing one can do is to get that factor of safety ratio for the case of 30 degrees and also for the case of 45 degrees. And if the slope angle in question is in between, and they can interpolate those factor of safety ratios.
Okay, thank you, Hossein. I have last one here, I guess. Any design guideline for 3D limited equilibrium method analysis?
Any design guideline for 3D limited equilibrium?
Yes.
So 3D limited equilibrium is just a method of calculation. It's not a design guideline, but what we calculate out of that has to comply with some guidelines which govern the project in question. So for example, if we are building an open pit mine or an embankment dam, and we have decided to use 3D limit equilibrium analysis, the design should be that the values we get out of that method satisfy the requirements which have been set forth by the Canadian Dam Association or the Openpit design guidelines.
Okay, thank you, Hossein. All right, I have more questions follow up, but I think it's because of limit of time, I will just choose the last one for you to answer. Yeah, like Alireza follow up one more question. Does is our example slide show displacement?
I didn't get the question, Lan. Can you please repeat?
Yeah, I think he's referring to one example, numerical simulation example you shown here. Did the SR one? Yeah, this example, did it show the displacement or the other parameters in this contour?
Yes. So the contours here are displacements, but when we try to find the critical slip surface or sliding mass, we can look at displacements, we can look at velocities, and we can also look at the contours of plastic shear strain. All of them will give us an indication of the critical sliding mass.
Okay, thank you a lot. Actually, I have a question. Yes. All right, go ahead.
Lang, just for your information and for the sake of the participants, I do have time if questions are coming in, but if you guys need to wrap up, the participants can always direct their questions to me and I'll try to answer them. Yeah, all right. Yeah, it'd be nice if you can just type your email here, and sure, anyone who wants to follow you up can send the email to you. Absolutely. All right. Can I ask one more question just about your computation method here? Yeah, as I mentioned, I'm available. So if okay, yeah, if there are questions, I'd be happy to answer them now. Good. Or if anyone has some burning questions, just feel free to unmute herself. I do see some experts sitting in this room, so just feel free to ask questions to Hossein. And my question is about, so for your strain softly defined in your simulation, did you encounter any strain localization? Especially, I think that's a very popular problem in finite element modeling. And that usually causes the divergence of the computation, which is not physical, but more related to the computational method. How did you justify your stability analysis is not caused by this type of divergence? Okay, so so that's a good question. As you mentioned, we do have a strain localization in many cases. Even when we have sometimes perfectly plastic models, we can see strain localizations. So that's certainly true. I'm not quite on board with the statement that those are not realistic, because when we do have failures in small scale or large scale, those also happen due to strain localization in many cases. So in many cases, we have to assess what we are getting out of our analysis and judge whether that corresponds to a sensible failure mechanisms. And for the cases that I have run in the past, that has always been part of the due diligence for the model. And in most cases, the results do make sense. And we, through comparison with different methods and different softwares and inspections, we have concluded that those are in fact reliable results that we are getting. Okay, thank you for your answer. All right, I don't think there's any more questions, but more than comments in the chat box, people can review afterwards. With that, if there's no one asking more questions. I see Masoud Rahju has raised his hand. Go ahead, Masoud. Oh, yeah.
Hello, hello. Thank you so much, Hossein, and great presentation. I have this question with regards to the 3D and 2D modeling. So the safety factor we get for 2D and 3D modeling would be different. And the guidelines provided given factor of safety that historically are related to 2D modeling, and that was basically adjusted to the 3D nature of the projects that engineers were dealt with. So my question is with regards to the safety factor we get from 3D modeling. Should we trust that more than 2D modeling? And how can we justify its use, which sometimes can be lower than the safety factor we get from the 2D modeling with regards to when we compare to the guideline values?
Yes, that's an excellent question, Masoud. So I mentioned there are cases where the factor of safety we get from 3D analysis is different from what we get out of 2D analysis with the same method even. So for example, let's consider this case where we have a pit which is essentially confining the sliding mass which is going to come down. When we do 3D analysis of a system contained like this, usually our factor of safety in 3D is higher than what it is in 2D. But that's reasonable because when we do a 2D analysis, we essentially assume that everything is the same. The profile is the same going into the page and out of the page indefinitely. Whereas in this case, we have a geometry which is more favorable than that. So in this case, I would certainly trust the results of 3D analysis more. As you mentioned, there are cases when the situation is reversed. For example, if we have a tailings pond, so essentially we have a ring inside it, we have some tailings, but it's going to slide out. For example, what happened for Mount Poly tailings dam. So that's the exact reverse of this situation where our 3D factor of safety may be lower than the 2D factor of safety. And again, the 3D model is capturing something which is real and physical. And again, I would consider the result of that 3D analysis more reliable.
Thank you very much. Thank you.
That answers at least part of your question.
Perfect. Thank you. Appreciate it.
All right, thank you for the questions, and also thank you for answer, Hossein.
My pleasure.
Let's see. Does anyone else raise their hands? No. All right, I think it's time to conclude. Oh, there's one more. I don't know whom. Oh, still Masoud.
Yes, another question I have. Okay,
Yes.
so very quickly, with regards to the strain softening behavior that you mentioned, a very interesting results, actually, I really like that. Now the question is, if in reality the behavior is strain softening, and then we adjusted, all the previous experience of failure mechanisms and failure occasions, and we proved our design based on real failure. So those safety factors are basically related to the cases that we get strain softening. Now, the question is that now the 2D models, linear, for example, linear limit equilibrium analysis that we do, and or for perfect plastic analysis that we get higher values. Now there is a ratio that you showed, and actually we have to multiply it to a value that that you get for the strain softening. Basically, all those guidelines, those values are kind of representative of strain softening behavior in some sense. So there is a kind of an adjustment to those values that we have to do when we do strain softening analysis.
Yes.
I'm not sure if I answered. I asked my question. I could ask my question completely or not, but based on your experience, please.
Sure. I think I understand what you're getting into, because my understanding is that, as you mentioned, normally these are done using conventional methods, limit equilibrium with perfectly plastic materials, and the design guidelines are based on that kind of procedure. Now, if we are going to use these new findings and multiply those factors of safety by those ratios, then suddenly we have some low factors of safety on our hand, which may not be compliant. So what do we do? I think that's the question.
Exactly.
My input is that we have had cases where this has not been considered, and catastrophic failures have happened as a result of it. For example, what happened with Aznalcóllar tailings dam in Spain? It was the worst environmental disaster in Europe. It's released a lot of really not good tailings into the environment, and that was because the dam was founded on a foundation which had some weak planes, and also it had strain weakening materials that had been observed during all the laboratory tests, but has not been considered for stability analysis. With their calculations, they were expecting that the tailings dam would be stable even under seismic conditions. They had to have a factor of safety higher than 1. And in reality, the tailings dam failed without any seismic activity. So that means that there is a big disconnect between what they calculated using those peak values and what the reality of the system was. We have, in my view, the same situation with Mount Poly. There was a layer of clay which was not identified in the area that the failure happened in the perimeter embankments of the tailings dam. And that material had some strain weakening characteristics to it. And unluckily, that layer was pretty much only discovered in the portion of the tailings dam which failed. It was not in other places, that specific layer. There were some other weak layers which had been identified, and the design of the tailings dam was adjusted for them for the main embankment, but under the perimeter embankment, there was this unidentified layer which did strain weakening, and as the result of that, Mount Poly failed. And that was also something close to a disaster. So we have understand that there has to be an adjustment to what we do as practitioners, but certainly we have had enough cases of failures that we need to reconsider how we do things. And in my view, we have to always go towards a more realistic representation of the materials that we are building with or building on.
Thank you very much for a comprehensive answer. Thanks.
Yes, that's a good answer. Thank you, Hossein. Actually, follow up that conversation. I'm not familiar with SRF analysis, but my understanding is you have to iterate this SRF value until the model becomes divergent. Do you think this can be sometimes become very computationally expensive if you have multiple materials or defined by different value criterion in your model, and or even you need to define different SRF for different material too, and any strategy to accelerate this process just to have a quick turnaround of the results?
Yes, and that's a great question, which is quite also useful practically. So I can share with you some of my tricks.
Okay.
So usually I look at problems with several degrees of sophistication. I start from relatively simple models and simple methods to get a feel for what the answer could be, the range that the answer will lie in. And then I start adding complexities that are required to be captured in the analysis to the model incrementally. And for each increment, I will check to make sure that everything is still working as it should. So in terms of computational expense of these models, so for example, the one that you see to your left, it will take close to a week for this model to give me a factor of safety. However, this is such a huge and important project that this kind of effort is absolutely justified for it. Now, what really controls the computational effort is the resolution of your mesh, sometimes the complexity of your models, but not necessarily the number of layers, because you will still have the same number of degrees of freedom in your system that need to be solved. But the number of degrees of freedom, which essentially means correlates to the number of zones or nodes that you have in your model. In terms of different shear strength reduction factors, we don't specify them directly. So for example, if you work with FLAC 2D or 3D or UDEC or 3DEC or RS2 or RS3 or Plaxis, essentially, when you do strength reduction calculations, you will ask the software to do it for you automatically. And the software will give you that critical strength reduction factor. However, it starts with a very wide range, and it narrows that range to kind of get closer to that critical value. One of the things that I usually do to substantially cut down on the computational effort is that I run some 2D analyses with different methods to get a feel for what that range could be. And then in the algorithm, you can specify what range of factors of safety do you look for to get that critical strength reduction factor. So when you limit it, the software has a much narrower range to look through to find your answer. So that's one way that you can substantially cut down on the computation time. And there's another one, which is the tolerance for finding it. So how close does the system need, the software need to go to find that? So maybe 3 decimal points of a factor of safety is not justified to look for. And in many cases, it's not meaningful at all. So maybe you can reduce that tolerance. So you can say, for example, if you are within 0.05 of the factor of safety, that's good enough for me. And then the system, once it reaches that point, it will not look any further. So those are two tips that I can give you to optimize your calculations.
Right, that's a very good answer. And thank you a lot, Hossein.
My pleasure.
All right, I think now it's time to conclude this presentation. And again, if you still have any questions, want to ask Hossein, just feel free to take initiative to follow up with Hossein through email. And also this recording will be uploaded to our YouTube channel. Feel free to visit. And with that, I just want to say thank you so much, Hossein, for spending time with us to give this wonderful presentation out of your busy schedule. And also appreciate everyone attending this seminar.